Okay, so 6-1, we did confidence intervals for a mean. So we found the mean. Yesterday you learned how to find the margin of error, and then you created the confidence interval with a certain level of confidence using those values on your z-chart. 6-2 is still confidence intervals for a mean, but the difference now is we will not know the population standard deviation, and that's really going to be the biggest difference. So if you read a problem that asks you to find a confidence interval, one of the first things you want to look for is, do I know the population standard deviation? You will always have a standard deviation, but we want to know if it's a population standard deviation or not. If it's not a population, then we're going to use this method instead, which there's going to be some slight differences. So instead of z values, we're going to be using t values if we do not know the population standard deviation. The formula is going to end up being similar, and I think you guys have this one on your sheet maybe somewhere. Yep. Okay, so if you look at this, this is how we calculated essentially a z-score, but now it's all sample stuff instead of population stuff for that standard deviation. So on top, we still have x bar minus our mu, our population mean, and then we're dividing by s over the square root of n. Remember, s over the square root of n was the margin of error that we talked about when we did our z-scores. So a t distribution is going to look similar to a standard normal distribution, a normal curve, with a few differences. So first, mean, median, mode are still going to be at 0 right in the middle. It's still going to be bell-shaped. It's still going to be symmetric about the mean. The total area under the curve is still equal to 1. Now, one of the bigger differences is the tails. So the far ends of the curve are going to end up being thicker. When we say thicker, we mean they're further above the x-axis. They're going to be wider on that area. The standard deviation of the t-distribution varies with the sample size, and that's that s over square root of n that we kind of talked about already with our z-scores. We also talk about something new now called degrees of freedom. So degrees of freedom, we don't really get into a lot with that in this course. For what you need to know now, degrees of freedom is the number of free choices you have left after certain selections are made. We have one set in our data values that we're using for all of these, so that means one choice is 10 made. So our degrees of freedom is n, our sample size, minus 1, and that's really all you need to know about it. There, you can get a lot more involved with that in future statistics classes, but degrees of freedom we're going to keep very simple and easy. It's just our sample size minus 1. As the degrees of freedom increases, then the tails get thinner. Okay, so the more degrees of freedom we have, which means the larger sample size we have, it's going to start to look more like our standard normal curve. So on mine here, it's in color. The blue one is our standard normal curve that we would see with like our z values. If we have 2 degrees of freedom, you can see what the curve looks like in those thick tails. Degrees of freedom of 5, you can see it starts to get closer and closer to that standard normal curve. Okay. All right, so t distributions today. Also put a little star by this guy here, circle it, highlight it, whatever. We're going to have a table that we're going to use in your packet. It's going to be t values, t distribution. If the degrees of freedom that you are looking for is not on the table, because every number isn't there, you're going to see it jumps over some, you're going to pick the closest number that is below that value on the table. So if you're looking for like 48 and 48 isn't on there, 45 will be the one that's closest. So you're going to round down to that closest one that you can find. All right, so finding critical values for t in your table. So mine's actually gold. All right, so in your purple packets, can you guys find the t distribution? I don't know what table number it is. Table 5 is the one you're looking for. Okay. All right, so we're finding a critical value of t, and then this value is what we're going to eventually use to find that margin of error and stuff and help us get those confidence intervals, just like we did for the ones for z. All right, so at the very top of this chart, it gives you a level of confidence. Again, it's giving us common levels of confidence here. And then to the side are our degrees of freedom. So the first example at the top, it says find the critical value, the t value, with a 95% confidence interval, and the sample size is 15. If the sample size is 15, that means my degrees of freedom is 1 minus that, so 14. So we find 14 on the side, we find 95% on the top, we find where they intersect, and you should see 2.145, and that would be the critical value of t that we would use for our margin of error, our sampling error when we do our confidence intervals. Okay, so the one below it, find a critical value at a 90% confidence level when the sample size is 22. If my sample size is 22, what's my degrees of freedom? 21. So we're finding where those intersect, 90% and 21, and you should see 1.721. Critical value of t. Okay. Questions using the chart? All right, moving on. Okay, margin of error formula for t. You can put this, I don't know if I had this on your paper, if you just want to write it down somewhere. It's essentially the same formula that we're using for our e values and our z charts. Okay, so margin of error is our critical value. We find the critical value a little bit differently here, but we get that value from our chart t. Standard deviation divided by square root n is still there, but this time it's sample standard deviation versus the population standard deviation. Good. All right, so let's practice finding the margin of error. So we need to be able to do critical value times standard deviation over the square root n. I have n, I have s. The only thing I'm missing is that critical value. Okay, so my c value is 95%, meaning a 95% confidence level. My n is 16, which means we're going to add a little extra to this. My degrees of freedom is, what's my degrees of freedom? 15. All right, so let's find that on our chart. 95%, 15, 2.131. Times standard deviation over square root of n, square root of 16. All right. We get 2.664. I'll give it 3 decimal places. All right, so my next one, 98% confidence level, standard deviation of 4.7, sample size of 9, degrees of freedom is 8. These are quick and easy little problems. 98%, degrees of freedom 8, takes me to 2.896 times 4.7 over the square root of 9. .537 margin of error. Okay. Questions so far? Really similar to 6-1. Okay. All right, so how do we calculate a confidence interval for a mean if we have a critical value of t? Again, these steps are very similar to what we did with the z-scores. Okay, so we're going to choose or be given a significance level that is our confidence level and our sample statistics s, n, and then an x bar. We're going to find a critical value of t in a two-tailed table using the confidence level and the degrees of freedom, which we just practiced. Find the margin of error like we just practiced, and then just like the last lesson, you're going to take the sample mean, add and subtract the margin of error, and you will get your confidence interval. Okay. All right, so let's do an example. You are currently selecting 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. Assume the temperatures are approximately normally distributed, and then interpret your results. Okay, so just like the last lesson, we want to make sure we meet one of two conditions first. Either A, my sample size is greater than 30, or B, my population is normally distributed. It told us here that they are normally distributed. Okay, so we meet that condition, we're able to do our confidence interval. The second thing that I always look at is the standard deviation. Here it is a sample standard deviation, so immediately in it I know it's going to be a T, not a Z. If it said population standard deviation, I would be using a Z score and critical values from that chart. Okay, so we'll have to find that critical value of T in a second. Other pieces of information I know in this problem. I know my N, my sample size is 16. I know, let's see, the sample mean, X bar, is 162. Do I know anything else? So the standard deviation is 10. These are all in degrees. And then I know that my confidence level, my C, 95% or 0.95. Okay, we could also add one more item to that list. If I have N, I also have degrees of freedom. One less than that, 15. All right, so let's get our critical value of T from our chart. So we've got a sample size of 15. We have a confidence level of 95. Find out where those intersect. I get 2.131. Okay. Next, we calculate our margin of error. Critical value of T times the sample standard deviation divided by the square root of n. 2.131 times 10 over the square root of 16. And I'm going to give it 3 decimal places, I guess. 5.328 degrees. Rounding with these 3 decimal places is always safe. You can kind of follow what they give you in the problem. Based on how they gave the sample mean and the sample standard deviation, they just rounded to 1 decimal place. That's why you see those point zeros. So if you just rounded to 1 decimal place here, that would follow the pattern of this problem, and that would be acceptable as well. Okay, but if you're not sure, just stick with 3 decimal places. More is always better. All right, once I have my margin of error, we're going to take our sample mean and we're going to add and subtract that margin of error on, which was 162 plus and minus 5.3, and then that's going to give me my confidence interval. Minus 5.3 gives me 156.7 degrees. And 162 plus 5.3, 167 degrees. Okay. Interpretation of that. So there are 2 ways we can word this. We can either say there is a 95% probability, or you can say that you are 95% confident, however you want to word that. So 95% probability, or you can say 95% confident, because that's our confidence level, that the population mean, that's always the thing that we're estimating here. We're trying to figure out what is the population mean of all coffees in all the coffee shops, is between 156.7 degrees and 167.3 degrees. Okay, so that is always what we are estimating in 6.1 and 6.2 is that population mean. That's what our interval represents. Okay, so hopefully it falls in there somewhere. Any questions on that problem? Okay, so last thing we're going to do, and then you guys will probably have some time to work on homework, is we're going to do a fun little create our own confidence interval, and you're going to be tested here. So you can do this in the margin on your paper, or if you want to scratch paper, that's fine. You are going to have 1 minute to write down as many states as you can out of the 50. Okay? Pull up the timer. All right. Are you ready? All right, ready? As nice as you can. Ready, set, go. $20 seconds. 5, 4, 3, 2, 1. Pencils down. All right, count them up. And put your number on the board with whatever you got. Count them up and put the number on the board. There's number 1 up there for me. That guy dead here, give it to me, right? Thank you. $29. Oh my goodness. Oh, that's impressive. 26.
Dang. Gracie sure wrote it bigger. Right. So I got 16.
Okay. All right, go ahead and write them down. And then you guys are going to answer the remaining questions on your packet. So you will need your calculator for a little bit of this. You are going to need to find X bar and S. Okay, not the other standard deviation S. You can use your calculator, put all the data in L1, or if you want to use a Google sheet, that's fine too. But you need to find those sample statistics yourself, and then we're going to find a confidence interval. We are assuming that this is normally distributed. Our sample size isn't quite at 30, so we're going to just assume that this is normally distributed and we're able to do this, okay? We're trying to find a 95% confidence interval for the mean number of states that senior students can name in 1 minute. Let's see what we can do. Bless you. All right. Here's what I got. So sample mean from the calculator, 18.6 repeating, or if you round it out to 18.667. Sample standard deviation, 5.538, and then I just made a quick little dot plot. Not quite normally distributed, but again, we have a small sample size, so we'll assume the population is. Okay, any questions on that? All right, and then on the other side, degrees of freedom you should have is 14. Critical value of t, 2.145. Multiply that by standard deviation over square root of n. Margin of error is 3.067. Add and subtract that to my population mean. I just used 3 decimal places there. I get 15.6 to 21.734. There's a 95% probability that the population mean of stat students will be between 15.6 and 21.734 states that they can name in 1 minute. What questions do we have here? Anything? Okay. All right. So you guys have the rest of the period then. You can work on, you have 20 minutes to work on 6-1 Math XL, which is due tonight. You haven't finished it yet. 6-2 Math XL is going to be due on Tuesday next week. So you've got 1 assignment due tonight, 1 assignment due Tuesday. You can start 6-2. You can get probably a good chunk of it done, and we'll finish that lesson up tomorrow then. All right. I'll do cell phone lotto for you.